Hi friends, the topic that we are going to look today is vector differentiation. For applying differentiation to a vector, we need an operator known as del operator, that is differential operator. Here it is, that is del is equals to I bar into dou by dou x plus j bar into dou by dou y plus k bar into dou by dou z. So it is the del operator and we use it for applying differentiation to a vector. Here is the two conditions. Those are f is a scalar, that means f is a function of x comma y, or f is function of x comma y comma z. And here it is, f is a vector, and that is f bar is equal to I bar into f1 plus j bar into f2 plus k bar into f3. So if you have a function which is a scalar quantity, what do you mean by scalar quantity? The quantity which has only magnitude, that there is no mention of direction. That means the here you can see the given function has only magnitude, there is no direction. So then it is known as scalar quantity. So here f is a scalar and here is f is a vector. That means what do you mean by a vector quantity? The quantity which has both magnitude and direction is known as vector quantity. And here you can see that f bar is I bar into f1 plus j bar into f2 plus k bar into f3. That means this vector is a directionable. That means it has I bar and j bar and k bar directions. So here it is a vector. Now when we apply del operator to a scalar quantity, what happens? Then it is known as grade f, that is gradient of f, that is del f, and we denote the grade f as del f. You can see here what you meant by del. I bar into dou by dou x plus j bar into dou by dou y plus k bar into dou by dou z. So it is del into f. We have to multiply with function f. So when we multiply function f with the del operator, what we will get? I bar into dou f by dou x plus j bar into dou f by dou y plus k bar into dou f by dou z. So the gradient f is del f, that equals to I bar into dou f by dou x plus j bar into dou f by dou y plus k bar into dou f by dou z. You can see here what you meant by dou f by dou x. Dou f by dou x is we have to derivative function f with respect to x. So it is a partial derivative. So we have to derivative f with respect to s by taking y and z are constant. And here you can see it is dou f by dou z, dou y. That means it is a partial derivative of y. So we have to derivative function f with respect to y by taking x and z are constant. So you can see here it is a dou f by dou z. So it is a partial derivative of f with respect to z. So we have to derivative function f with respect to z by taking x and y are constants. So when we apply del operator to a function f, we get del f. And let's see what will happen when del operator is applied to an vector. When we apply del operator to an vector, we have two concepts, that are divergence of f bar, that is del dot f bar, and curl of f bar, that is del cross f bar. So these are the two concepts that we have when we apply del operator to a vector quantity. So here you can see that is del dot f bar means, what do you mean by del? It is I bar into dou by dou x plus j bar into dou by dou y plus k bar into dou by dou z dot I bar into f1 plus j bar into f2 plus k bar into f3. What is this? This is f bar. What we have taken? F bar, I bar into f1 plus j bar into f2 plus k bar into f3. So we have del dot f. So when we apply del dot f bar, we get dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. So when we apply an del operator to an vector, we have dot product and as well as cross product. So next, curl f bar is del cross f bar. So how to calculate the del cross f bar? That is determinant of I bar, j bar, k bar, and here is dou by dou x, dou by dou y, and dou by dou z, and the functions of In the function we have f1, f2 and f3. So determinant of these we get curl f bar. So after determinant we get I bar into dou f3 by dou y minus dou f2 by dou z minus j bar into dou f3 by dou x minus dou f1 by dou z plus k bar into dou f2 by dou x minus dou f1 by dou y. So when we apply a del operator to any vector, we have del divergence of f bar and curl f bar. So when we apply grade f, we have normally the problems came into existence of grade f is here. Normally the problems are based on grade f, that means del f, and normal vector. Normal vector is also known as del f. That means grade f is the normal vector of f. And unit normal vector is denoted as E cap, and E cap is del f by modulus of del f. So when we have unit normal vector, so we can calculate it by using this formula, that is E cap is equal to del f by modulus of del f, and here it is angle between two functions f1 and f2 at a point. That means when we have a problem that is based on angle between the two functions, that means the question gives two functions f1 and f2 at some point. So we have to calculate the angle. So in that way, we have to calculate cos theta is equals to del f1 into del f2 by modulus of del f1 into modulus of del f2. So we have to calculate del f1 and del f2 and modulus of del f1 and modulus of del f2. So we get the angle theta. So you can see here what you meant by del f1. So del f1 is n1 bar, that is normal vector, and dot del f2 is n2 bar. So it is normal vector n2 bar. So del f1 into del f2 is, it is not into, it is a dot product. So I have to dot product of two normal vectors for the functions f1 f2. You can see here it is a normal vector. How can we calculate normal vector? N1 bar, so n bar, so normal vector n bar is equal to gradient of s, that is nothing but del f. So you can also here you have to calculate the angle between the two functions at a point. So we have to calculate cos theta, that is del f1 into del f2. Del f1 is nothing but n1 bar and del f2 is nothing but n2 bar, and by del f modulus of del f1 and modulus of del f2, that is n1 bar and n2 bar. Next we have a problem, that is angle between the functions at different points. That means we have here we have two functions at a single point, but here we have only one function but at different points, that may be 2 points. So we have to calculate the normal vector at one point and then the normal vector at another point. So we get n1 bar and n2 bar. We have to dot product and between the two functions, and we have to take the modulus of n1 bar and modulus of n2 bar, then we will get the angle between the two functions at different points, means two different points. And next we have a problem like this. Two functions are orthogonal, then we have to calculate n1 bar dot n2 bar equals to 0. That means if we have a problem in which two functions are orthogonal, then we have to dot product of the normal vectors of the two functions. Here what is n1 bar? Del f1, and what is n2 bar? Del f2. So we take the condition is del f1 dot del f2 equal to 0 for the functions which are orthogonal. And next we move on to the divergence. Here we get a problem is like check whether the vector is solenoidal or not. Then we have to calculate del dot f bar equal to 0. That means we have to calculate del dot f bar. So if we get an answer is 0, then we confirm that the vector is solenoidal. Then if we not get a 0, that means any other value, then that vector is not a solenoidal vector. And we would move on to curl. When we have del cross f bar is 0, that means if we get an answer 0 when we calculated del cross f bar, then that vector is irrotational. That means the vector is irrotational. So if we not get a 0 as answer, or we get a any answer which is not equal to 0, then that vector is not a irrotational vector. So here are the two conditions when we have del dot f bar and del cross f bar. If del dot f bar is 0, then that vector is solenoidal, and when the del cross f bar is 0, then that vector is irrotational. These are the basic problems that can we get in these concepts. So you can see here when we apply del f, we get the del f as vector quantity. So here the function is a scalar quantity, but when we apply del f, that is gradient of f, then the function is converted into vector quantity. When we apply del dot f bar, so then we get scalar quantity, means that given vector is converted into scalar quantity, because this del dot f bar doesn't contain any I bar or j bar and k bar, so it is a scalar quantity. So when we want to convert an vector quantity into a scalar quantity, then we just apply del dot f bar, and here vector quantity is same as vector quantity we get. So here is the basic same problem that can we get in our examinations based on this concept. And next we will see the main concept that we get in gradient of f is directional derivative. Let's see. So here is the directional derivative of function f, then it is denoted as del f. So as we have seen earlier, that is grade f is also denoted as del f, and normal vector is also denoted as del f, and the directional derivative of the function is also denoted as del f. And the problem that can we get in our examinations based on the directional derivative is directional derivative of f in the direction of e bar. So we have to calculate the directional derivative of f, that means del f, in the direction of e bar. That means we have to calculate del of in the direction of e bar. Then we have to take del f dot e cap, where e cap is e bar by modulus of e bar. So what is e bar? That e bar is given in question. So we have to calculate the unit vector e cap. That unit vector e cap is e bar by mod e bar, and after calculating e cap, we have to dot product del f dot and unit vector e cap. And next is directional derivative of f in a direction normal to the surface g. So here we have the function f, we have to directional derivative of f means del f. We have to calculate in a direction normal to the surface g. So here also you have to calculate del f dot e cap, but here e cap is del g by del g, mod del g. So what is del g? That we have seen in earlier, that is del g is nothing but normal vector. So here del g is nothing but normal vector. Why normal vector? Because here we have direction normal to the surface g, that which is nothing but normal vector of g. That's why we have taken the normal vector del g for unit vector. So e cap is del g by modulus of del g. Next we have directional vector of f along tangent to the curve, that is del f dot e cap. Here the curve is having the points x, y and z, which are the functions of t, and we have to take directional derivative of f, that is del f along tangent to the curve is del f dot e cap, where e cap is dr bar by dt by modulus of dr bar by dt. Here r bar is xi bar plus yj bar plus zk bar, because any point in a vector we have x comma y comma z, then that positional vector is r bar, so that r bar is xi bar plus yj bar plus zk bar. So we have to find out the tangent vector of this position vector, then we can take dr bar by dt. That is the tangent vector to the curve. So dr bar by dt is equal by 1 modulus of dr bar by dt. Next, we have directional derivative of f in the direction of line PQ. Then we take del f dot e cap. Here PQ is a points, this P and Q points. Then we have to take del f dot e cap for the directional derivative of f in the direction of line PQ, where e cap is PQ bar by modulus of PQ bar. Here PQ bar is OQ bar minus OP bar. So we have the positional vectors are OQ and OP. If we subtract, if we positional vectors OQ minus OP bar, we get the line vector, that is PQ bar. So these are the basic problem that can we get in our examination based on directional derivatives. So let's recap all these types. Here all the solution is del f dot e cap, but the variance is e cap is here we have e bar, so the vector is there, so that's why we have taken e bar by mod e bar. Here the direction normal to the surface G, because it is the normal vector of G, that we have to take del G by mod del G. Here tangent to the curve is there, that's why we have to take tangent vector, that is dr bar by dt. Here we have the line PQ, so we have to take the line vector, that is PQ bar. So PQ bar is OQ bar minus OP bar. So in this way we have to remember all these things to do the problems. In next video we will solve problem based on this concept.